Okay, hello Professor. I'm going to be solving through this problem. So we start off with this equation. Obviously, the system shown, water is pumped from tank 1 up into tank 2 through 1,500 feet of cast iron pipe at 360 feet cubed per minute. The exit from tank 1 and the entrance to tank 2 are both sharp-edged and both elbows bend at regular radius and are threaded. If height C2 equals 225 feet, measured from the same reference height as C1, calculate the power that the pump delivers to the water. Okay, so reading through just really quickly what I get out of this, we have here tank 1. Obviously it is open, free surface, same as tank 2. This would be tank 2. And then we do have this pump here in the middle, which appears to be a centrifugal pump. So what I get out of this problem statement is that my diameter of the pipe is 8 inches. My flow rate is 360 feet cubed per minute. And my height, Z2, is 225 feet. Okay, so what's going on in this system is water is flowing from tank 1 into this pipe here. It is then going to pass through this pump, which should have some rotating shaft or impeller, which will cause it to be projected forward back into the pipe again. It is going to pass through this elbow here and this elbow there, which in the problem statement it tells us that they are regular radius and threaded. That is important. And then it is going to flow back into this tank too, and again be exposed to the surface. Really quickly, the entrances to the tanks are relevant. It says here that the exit from tank 1 and the entrance to tank 2 are both sharp edged. So we know that this entrance here is going to be sharp edged and this exit here is going to be sharp edged, which will come into play when we talk about the minor losses. So kind of working backwards through fluid mechanics, we first need to talk through a few pieces of information which are relevant in this problem. So this is a pipe flow problem and a pump problem. Really quickly, as we learned previously in class, when liquid flows through pipe flow or through a pipe, it could either be a turbulent flow, a laminar flow, or a transitional flow. So we have turbulent flow being, imagine this is our pipe here. The flow is going to go, I would denote the liquid as peach color, sure. It's going to go a little bit everywhere. It's not going to be steady flow. Well, it is steady flow, but it's just moving. No, actually, yeah, this is unsteady flow. And then laminar flow, which is going to be more smooth than turbulent flow, right? So this flow is more steady. It doesn't have all this crazy commotion going on. But what exists in both of these types of flows in a pipe, these pressures due to viscosity from the fluid, and then we also have this shearing force, tau. As the liquid passes through the surface, there is going to be some shearing stress from the liquid due to friction. Okay, so in the turbulent example, the shear stress is a function of density. Right, so the turbulent flow, the flow is going to be, the shearing stress is going to be a function of density, and in laminar, the shearing stress is going to be a function of Now here we are talking about the shear function of, well, this is actually not a function of rho. Okay, and we have been giving equations in the past. Laminar flow is what we have previously worked with because this is steady flow. So laminar flow is something that we are very familiar with and we have previously solved for shearing stresses. This is just going to be your basic tau equals the viscosity times du over dy. So you can see that this laminar flow is in fact a function of viscosity and not of density. And then this turbulent flow was defined in the textbook to be rho times the mixing length squared du over dy squared. So as you can see, this is a function of density, and then laminar flow is not a function of density. So the only fluid function that laminar flow is dependent of is the viscosity. Okay, so that's turbulent versus laminar flow. Through these pipes, due to these flows, there is going to be some major losses and minor losses, which we need to consider. So, major loss, I will write out here. Major loss is the head loss from the viscous effects in the straight pipes. So this fluid is flowing through this pipe, and as mentioned earlier, there is going to be some shearing stress and some head loss here due to friction. So that is what major loss is defined as. Major loss exists in every pipe, even if, well, let me write what major loss is. Head loss due to viscous effect, and I'm just pulling this information out of the textbook. But I did want to just go through these definitions really quickly before solving the problem because they are important. And then minor loss. Minor losses are going to be due to everything else but the straight pipes, essentially. So from the head loss from pipe components, such as an elbow, a flange, a T, a valve, or it could even be the pipe exit and entrance. So head loss due to pipe components. Okay, and these together will be the total loss. So head loss will be the minor head losses. Total head loss is equal to minor head losses plus major head losses. Okay, and then again, major loss exists in every pipe because in every pipe there is going to be interaction between the fluid and the pipe causing some viscous effects. This is all due to the no-slip boundary condition, which we learned previously in the course. The no-slip boundary condition says that fluids will interact with the surfaces that they touch, so they can't just go through a pipe and not react with the wall. There's going to be some friction or some force due to the viscosity of the liquid and some shearing stress along the wall. Minor losses, not every pipe will have, or it may have more minor loss than it does major loss, vice versa, depending on the way the pipe is. And then we do have the equations for major loss and minor loss to be the major. For major losses, we will have to use this friction factor again because of the viscosity effects, times the length of the pipe over the diameter of the pipe times the velocity squared divided by 2 times the gravity constant in either English units or metric. And then for the minor head loss, it is going to be defined by this constant, K sub L, which is the loss coefficient for each component. So for an elbow, it'll have a certain value. For a T, it'll have a certain value. So this is the loss coefficient, and this loss coefficient is actually dependent on the geometry of the shape, right? If it's a pipe, if it's a T or a valve, and Reynolds number. Again, Reynolds number being, oops, rho Vd over the viscosity. Okay, and then continuing on with the equation, K sub L times the velocity of the liquid through the pipe squared times 2 times the gravity constant. So those are the two equations that we will be utilizing along with this total head loss. Last thing, what else do we have to go over? This is just the definitions. Oh, this pump. The pump is its own system, essentially. So it is going to be this exit and entrance. Within this pump, we will have a rotating shaft. So it's going to do work on the fluid from point 1 to point 2. So the fluid is going to travel through this pipe. Work will be done onto it. It'll be impelled and then be released from the exit. So this pump is considered a turbo machine, which we learned in class, and it will do work on the fluid, which in this case will be water. Okay, so this pump is going to produce some power, right? There is work being done, so we are going to define a few equations. So for the pump, there is going to be an actual head, which is going to be the shaft work minus the pump head loss. So shaft work minus head loss. So that's going to be the actual head of the pump. We'll do actual head. Okay, and then another equation that we will use for this pump, I will write in green. The power equals rho G Q and then HA, which we defined over here. And this is the power done on the fluid by the pump. So we would do the density times gravity times the volumetric flow rate times the actual head of the pump. And we are going to also use this equation. Okay, lastly, since this is a pump, we do have to modify Bernoulli's equation a little bit to be able to analyze, which I will just go ahead and add here really quickly. So Bernoulli, we do have P1 over gamma plus B1 squared over 2G plus Z1 equals P2 over gamma plus Z2 plus V2 squared over 2 gamma. Okay, and there is going to be some head loss produced by these two tanks in the pump, so we're going to have to add the head loss. We could subtract it from the left side, but we can also just move it to the right side. And then we are going to subtract the head added by the pump, so the pump is going to add some head. So this is the equation that we are going to use. And then again, I didn't define head, but head is equal to the delta pressure divided by the specific weight, or delta pressure divided by rho G. So that is what it's referencing that's what we are referencing when we say head. Okay, so that's enough of the equation defining definition talk. Going back to this problem, so we do have these two pumps. I'm going to go ahead and define 2 points. I'm going to define point 1 and point 2 for use later on in Bernoulli's equation. So I'm going to define point 1 to be right here on the surface. Being that it is open to the free surface, it would go ahead and utilize that the pressure is 0 at that point. And then again, for this side also, pressure is going to be equal to be 0 because we are open to the atmosphere. So the problem is asking us to calculate the power that the pump delivers to the water. So based off of reading this, I'm going to utilize the equation that I defined. PF is equal to rho G, what is it? Rho GQ HA for the pump. And yeah, I think that's about it. I am going to go ahead and define some variables for use, not variables, some constants for use throughout this problem solving. And these are just pulled from the book, but I do want to go ahead and just list them. So we have the roughness of cast iron, right? This is just pulled from a table in the textbook, is 8.5 times 10 to the negative 4 feet. Rho is equal to 1.94 slugs per foot cubed. Mu, which is the viscosity, is equal to 2.34 times 10 to the negative 5 pound-second per foot squared. The specific weight of water is 62.4 pounds per foot cubed. The absolute viscosity, which I'm not sure if I'm going to use, but I'm just going to go ahead and list, is 1.21. Actually, I'm not going to list that one. And then I do have the loss coefficients for the elbows, K sub L for elbows. K sub L is equal to 1.5 for a threaded elbow, 90-degree threaded elbow. For the entrance, pipe entrance, and what I mean by entrance is in tank 1, let me go back. Tank 1, we are going from this large tank into the pipe, so that is the entrance to the pipe. Pipe exit will of course be exiting the pipe when we go in. When we enter tank 2, we are exiting the pipe. So that is what I mean when I'm saying entrance and exit. So the entrance, K sub L. In the problem statement, it did say it is sharp edged, so I just looked up the loss coefficient for sharp edged entrance, and that is going to be 0.5. And then the exit, K sub L, is going to be 1.0. Okay, so that's about all of the constants that I will be utilizing throughout this problem solving. So we'll just go ahead and section that off. Okay, so we are given Q, which is our volumetric flow rate. So with Q, I can go ahead and solve using continuity. Q equals VA. I can go ahead and solve for the velocity. And then using continuity, we do know that Q1 is going to equal Q2 at the both points that I selected. A1, which means A1 V1 will be equal to A2 V2. And since the area and diameter of the pipe is the same throughout, this area is going to be constant, which means V1 will be equal to V2. So when I solve for this V, this will also be V2. So V is going to be equal to Q over A. Q we did find to be 360 feet cubed per minute. And then my area I know is pi over 4 times the diameter squared. My diameter is 8 inches, which I will divide by 12 to turn into feet squared. Okay, and then from this, we do get 1,031 feet per minute. I want this in feet per second, so I get 17.19 feet per second as my velocity for point 1 and point 2. Okay, so this number is important. We will be using that. So that's my velocity through the pipe. Next, I can go ahead and solve for Reynolds number. Solving for Reynolds number will help me to define whether the flow is laminar or turbulent. It could also be transitional, but in this class, we are not using transitional. We're not studying transitional flow, so it will either be laminar or turbulent. So that is why we're using Reynolds equation to do the dimensionless analysis. Rho VD over mu. And really quickly, before I actually solve for Reynolds number, there is one thing I forgot to define. So the flow will be laminar if the Reynolds number is below 2100 or about 2000. And it will be turbulent, and for purposes of this class it will be turbulent if it's above 2000, but it actually would be if it's above 4000, just because I'm eliminating the transitional flow. And then I did include these diagrams here for when I did talk about these things from the book. So you see that Reynolds number at 0.2000, it does end the laminar flow. So from 0 to 2000 it will be laminar. From 2000 to 4000 the flow will be transitional, if that's what the Reynolds number is. And then anything above 4000 the flow will be turbulent. So that's where these numbers are coming from. Here Reynolds number is defined as velocity times diameter divided by absolute or specific volume. Is that specific volume? Yeah, specific volume. But I'm using Reynolds number to be rho VD over mu. So solving through, we have rho is 1.94 slugs per foot cubed. My velocity is 17.19 foot per second, which I found earlier. My diameter, again, divided by 12 to make it in feet, 8 over 12 feet. And my viscosity, which I found in the textbook, was defined to be 2.34 times 10 to the negative 5 pounds second per foot squared. Okay, I do want to include the conversion that 1 pound is equal to 1 slug foot per second squared. So solving through for that, first in terms of units, I will be left with slugs foot second on top divided by slugs foot second on the bottom, which will all clearly cancel. And the reason why I included this is because Reynolds number is a dimensionless analysis, so being able to cancel these dimensions is crucial. Otherwise it would not be valid to solve for Reynolds number if a dimension was present. So solving through for this, I do get a Reynolds number, a 9.5 times 10 to the 5th. And referencing these notes here, Reynolds number is very well over 4000, which means that the flow is in fact turbulent. So my flow is going to be, when I reference turbulent region, when I reference this graph, my flow is going to be somewhere from here to wherever 9.5 times 10 to the 5th is. And again, this turbulent flow is unsteady, and it's going to have, as noted here, random turbulent fluctuations. So it is going to, we can expect for this to continue to be squiggly until we get to the actual Reynolds number that we solve for. Okay, so from this Reynolds number, being that this is turbulent, going back to my notes, where was it? Okay. So being that this is turbulent, we will have to calculate a friction factor. This comes into play when we calculate the major losses, because major loss has some friction going on. For turbulent flow, I did not include this here. For turbulent flow, the friction factor will be found on the Moody diagram, because the turbulent flow is more so dependent on the roughness and the density due to the shear stress. And then the laminar flow, we can find the friction factor simply by dividing that 64 divided by the Reynolds number. But we are turbulent, so this is going to rely on a Moody diagram. Okay. Again, no, sorry, going back. Okay. So in order to find the friction factor, we do have to reference this Moody diagram. As you can see, this right side has sigma over d, so the roughness over the diameter, and then the Reynolds number in the x. So we know our Reynolds number. We do have to solve for sigma over d in order to get our friction factor. So sigma, which is our roughness, divided by the diameter, is equal to 8.5 times 10 to the negative 4 feet, divided by 8 over 12 feet. From this, we get 0.001275 for that constant, and we can go to this diagram, plug in that. So if you look closely here, we have this 0.001. So I do know that I am going to be somewhere around this on my Moody diagram following this curve. And then you just simply take your ruler down to where the Reynolds number is. So I'm at 9.5 times 10 to the 5th. So I'm going to be somewhere around here, right there, which I actually plugged into my calculator, or to a friction factor calculator, to get that my friction factor is equal to 0.021. And you can calculate this using the Moody diagram and or plugging it in to an equation. I believe it is called Coleman's equation. Colebrook equation, and then this friction factor is obviously a function of Reynolds number and the roughness over the diameter for turbulent flow only. Again, emphasizing that laminar flow is not dependent on the roughness or the density of the fluid, only the viscosity. So as in turn, it is dependent on the diameter but not on roughness, because the flow is smooth compared to the turbulent flow, which is just all over the place. Okay, so solving through for that. We can now move on to solving for our losses. So for our major loss, which again is due to the flow through the pipe, straight pipes, we have head loss is equal to the friction factor times L over D, V squared over 2G. So this will be equal to 0.021. The length is 1,500 feet, divided by 8 over 12 feet, times 17.19 foot per second squared, divided by 2 times gravity, which is 32.2 foot per second squared. Here I get 216.8 feet due to my major loss. And now for my minor loss, I will have to calculate for all the different components, which would be 4 total, 2 elbows, and then 1 entrance and 1 exit into the pipe. Okay, so for my major loss and the elbows, H sub L is equal to K sub L, V squared over 2G. K sub L I was said to be 1.5. Velocity divided by 2 times 32.2 foot per second squared. And we get 6.88 feet, which I will be multiplying by 2 when I sum all of the minor losses. The entrance into the pipe is going to be loss coefficient of 0.5 divided by 2 times 32.2 foot per second squared. And then here we get 2.29 feet. And then my exit, which will be 1.0 times 17.19 foot per second squared, divided by 2 times 32.2 foot per second squared. Here I get 4.59 feet. Okay, so summing all of my losses, I will get that my total head loss is equal to my minor losses, which are going to add to 20.64 feet. This is my minor, plus in purple here 216.8. This is my major loss. So my total head loss is going to be a whopping 237.44 feet due to all 4 components and due to the friction in the pipe. Okay, so this is going to be used in the following equation. Again, I wrote Bernoulli's equation down for the pump. So that is what I'll be using. So next step will be Bernoulli. From point 1 to point 2, both of my open tanks. So restating the equation, P1 over gamma plus Z1 plus V1 squared over 2G is equal to P2 over gamma plus Z2 plus V2 squared over 2G plus my head loss minus the head rise from pressure, the pump. Okay, so right off the bat, we know that P1 and P2 are both going to be equal to 0 because they are open to the atmosphere. V1 and V2, as mentioned earlier, due to continuity, they will be equivalent, so these two will cancel. Additionally, we would know that since it is a large tank, we can just assume this velocity to be 0. Okay, and then rearranging, we do want to solve for HP, which HP is actually, as I mentioned earlier, the H actual, so that this is the head due to the pump. So HP will be equal to, moving everything over, Z2 minus Z1 plus the total head loss. Okay, Z2 was defined in the equation to be 225 feet, and since it is at the same reference point as Z1, I'm just going to go ahead and use each as their own value rather than moving my datum. So then Z1 will be 100 feet. And my total head loss, which I found above, to be 237.44 feet. Okay, so adding and subtracting these, we get 362.44 feet. This is the total head due to the pump. Okay, and we can go ahead and plug this into the equation for power done on the fluid, work done on the fluid. Rho G, this is actually Q, not H. So plugging this in, we get 1.94 slugs per foot cubed times 32.2 foot per second squared. Q is given in foot cubed per minute, so I just went ahead and converted that to foot cubed per second. So it'll be 6 foot cubed per second. And then my actual head rise due to the pump is 362.44 foot head loss, sorry. Okay. And then I am going to do a small unit conversion here. Solving through these numbers that I put, the units will turn out to be slug foot per second squared. Again, I'm just doing unit verification for purposes of correctness. This foot cubed slug foot per second squared is actually a pound. So we get pound times foot per second, which is foot-pound per second, which is a unit of power in the English system. So that proves that. And we will get a number of, or a power. About 135,000 foot-pound per second. Converting this to horsepower, again, we just divide by 550. This is equal to about 247 horsepower. So I have both units. So this is, in summary, the amount of power that the pump will deliver to the water. That's about it. We just summarized. Initially, I summarized through the concepts, basic concepts of all of this pipe flow. And then we went through the minor losses and the head losses. Bernoulli's equation was modified a bit to accommodate for the turbo machine, aka the pump, which is a centrifugal pump. And then we just went through and solved. Calculating my units, I was able to correctly see that I solved for the correct unit at least. Hopefully the answer is right. But yeah, I'm going to go ahead and sign. This is terrible. My name. Again, my name is Isabel Marikia. And that's about it. This is probably the longest video ever, but thank you, Professor. I hope you have a good summer.